So we'll go ahead and get started. Chapter 2 cover slide looks like this. And we talked about kind of the Earth as a system. So remember, the Earth has the geosphere, and around the geosphere, held by gravity, is the atmosphere. We can have the biosphere. The hydrosphere is the fourth one. So you can almost kind of see all of that a little bit in this slide. Okay, so we're going to talk about temperature really in Chapter 3, but in Chapter 2 we're going to kind of introduce some different things about temperature. But why do we have the temperature that we have? Well, it kind of depends upon your location to a certain extent. You guys would say near the equator temperatures are going to be warmer, and near the poles temperatures are going to be colder. So that generally is called latitude. Okay, so that's our latitude. Also, altitude, which is just a couple letters switched from latitude, right? Oh, wait a minute. Did I give you your Chapter 2? No. You guys are so nice. Just too nice. This is nice. Okay. There you go. Sorry. My bad. I would have eventually caught on. So altitude, which to me the word itself looks very similar to latitude. Altitude is elevation. So you guys know as you climb a mountain it gets colder. Yeah, exactly. So never forget what you already know when you come to a class like this, right? Well, other reasons that your same location, we'll talk about different other things about location too in Chapter 3, but other reasons that you could have your temperatures vary actually depends upon what season you're in. You know, summertime it's warm, okay, wintertime it's cold. And of course season has to do with the Earth orbiting the sun, so we'll be talking about that. And then actually not until, I think, Unit 3 maybe, do we talk about this concept of an air mass. But honestly, air masses are definitely a player because, you know, when we have those really cold temperatures all of a sudden, basically a chunk of air that sat over Canada or even the Arctic has come down. It sat over there for a couple weeks, it got cold, and then it came on the move, okay? So an air mass can come into our area and just make you cold. Alternatively, we could have an air mass from the south, you know, move up, and then, you know, it sat over there for a while, got warm, and the air mass goes on the move, okay? So those also can kind of change your temperatures. So we need to talk about the Earth as it has two motions, and these are motions that you're already, I'm sure, familiar about. Okay, it rotates or spins on its axis of rotation. Notice I capitalized the fact that the Earth's axis of rotation is tilted. And let's see, do I have I think I might have moved it. I used to have a yardstick in here. I was just too efficient that way. Okay, but when you buy a globe, okay, you can see it very good, but its axis of rotation is like, it goes, here's the South Pole, here's the North Pole, so it's tilted. Okay, specifically that tilt is what we say, like this slide says, 23.5 degrees. To me, I kind of count that angle as being, if you were to take that tilt and go straight back up, okay, it would be like basically its stick, its axis would be perpendicular to how it goes around the sun. Okay, so then you tilt it 23.5 degrees from that angle, okay, and that's the 23.5 degrees. So this is the axis of rotation, this is straight up and down. So it's tilted 23.5 degrees. And I'm going to try to convince you, you probably already know, but it's that tilt as it goes around the sun that actually gives us our seasons. When we look at other planets, if they have seasons or don't have seasons, if they have a tilt, they have seasons. If they don't have a tilt, they don't have seasons. Okay, so that's kind of how that goes. So the Earth spins once every 24 hours or so. And this year is a leap year, right? Is that not cool? In February we have 29 days. Yep. So we kind of make up for the little extra time it takes for the Earth to complete one rotation on its axis. So the Earth, there's a lot of R's. The Earth revolves and orbits are the same. So the Earth orbits or revolves about the sun. or orbits the sun, revolves about the sun. And it takes 365, now that's why we have a leap year. It's not the rotate spinning on the axis. It's about 365 and a quarter days to complete one trek around the sun. So every 4 years we get a leap year. And then there's some other strange thing where we don't get a leap year. I think every 1,000 years or something. I don't know. I should look it up. So here is a picture of the Earth at 4 different locations as it orbits the sun. Okay, so a few things about this little figure here. Okay, first off, can you see, and it's kind of small, but I'll pick on July here. Can you see the tilted axis of rotation? Here is the South Pole, and here is the North Pole. That's the axis the Earth spins on. So let's see, it's all about counterclockwise. So after July, we're going this way. And notice if you take 12 months and divide it by 4s, because we have 4 positions up here, this takes 3 months to go to get from position A to position B. Okay, and notice that the tilted axis of rotation is right here, and then 3 months later, it's the Earth is over here. The axis of rotation, I'll kind of exaggerate it here, and then 3 months later, it's here, and then 3 months later, it's back here. Okay, so the tilted axis is always actually pointed kind of in the same vicinity. And I know this is not about stars, but if I were to put a star up here, would anybody know what star this axis points to? The North Star. That's not I'm not being facetious. It is the North Star. So what is another name for the North Star? Starts letter P. Oh, you guys need to, yes, Polaris, you guys need to take astronomy. Yep. So as the Earth orbits the sun, it seems like its axis should be pointed to a different star, but those stars are so far away that actually ends up being the same star. It's Polaris. But just right away, we're cold in January, right? Okay, so notice that actually in January, we're going to call it the circle of illumination. This right here, okay, that's kind of, this side gets lit, this side is dark. Or well, anyway, it's nighttime as it's being shown there. But can you see where as the Earth spins on its axis and it goes counterclockwise too, okay, as it spins on its axis of rotation, up there at the North Pole, it's dark, it's just dark. And actually there's been a vampire movie about that too. Like if you're a vampire and you need to be dark, then there's where you want to go when that season is having winter. So a few more things about this. As far as terms, sometimes I put terms on your unit exams, right? So you see the plane of the ecliptic, that's kind of like if this is the sun, okay, if I'm the sun right here, the Earth kind of goes around in kind of a plane, okay, that's that. And actually all of the planets, including the 9th planet, okay, you guys hear about they found a 9th planet out there? Beyond, yep, the 9th planet, they think it's similar in size and maybe composition to Uranus and Neptune. So, we'll see. The other thing, as far as terms go, actually, the sun is kind of offset from being the center of the planets orbiting. It's at what we call perihelion, or sorry, not perihelion. It's all at what we call one focus of each of the orbits of the planets. So here, actually, it's closest. Okay, we call that perihelion. Okay, so notice this. Actually, the Earth is closer to the sun closest in January 3rd. We just passed perihelion. Okay. And it's farthest here at aphelion. Farthest. So that was the Earth rotating on its axis and the Earth orbiting the sun. So I know they're kind of hard to see, and so I don't know how you guys want to do this, but when I said note their main lines of latitude. So now lines of latitude, for instance, the equator is a line of latitude, okay? We up here are about, can't remember, I think we're about 42 north latitude, something like that. Okay, so there's a latitude. So important lines of latitude are the Arctic Circle, so that's at 66.5 degrees north. The Tropic of Cancer at 23.5 degrees north, and the equator. And then going down, we have the Tropic of Capricorn, 23.5 degrees south latitude. I'll put these next to it. The Arctic Circle, I said, was 66.5 degrees north. The Tropic of Cancer, 23.5 degrees north. The equator, what's the latitude for the equator?
0.
0, perfect, yep, 0 degrees, yep. The Tropic of Capricorn is, again, 23.5, but it would be south, 23.5 degrees south. And not shown on here, and I don't know why, I'll go ahead and draw it in, is, again, if you're a vampire, you would want to make sure that you were aware of this 66.5 degrees south latitude, and that is called the Antarctic Circle. Antarctic Circle. So those lines of latitude are kind of important when it comes to seasons and stuff. The other thing, and you probably, maybe want to kind of read your book to reemphasize how this all works, but you probably heard of the summer solstice and the winter solstice. Okay, so the summer solstice is right here. I'm going to put summer solstice. And I guess the reason they left it blank is it's summer for us, but what is it for the southern hemisphere?
Winter.
Winter solstice, yeah. But the important thing, and I put summer solstice, is it's kind of the most, let's see. I'm going to go ahead and make this the sun. The important thing about the summer solstice is the sun. And I usually make that clock Polaris, so if you can see my tilt, it's kind of right here, okay? So this is basically, we put day and night there too. This, that's not gonna work. This is my summer solstice, okay? So the Earth is most tilted, the northern pole is most tilted toward the sun, okay? And then after summer comes fall, okay? So this is fall. Actually, we have 2 equinoxes. This is a fall equinox, and this is the winter solstice. Okay, this was where actually I said if you're above the Arctic Circle, 66.5 degrees north latitude, then actually as the Earth spins, the sun never rises. Okay, so that is the winter solstice. Then after winter we have spring, so this must be a spring equinox. Okay, equinox. At both of the equinoxes, as the Earth spins, all latitudes get equal equinox. They get equal hours of daylight and nighttime. So if you split 24 and a half, that's 12 and 12. And we go here. So summer solstice for location A. And then the Earth continues to go around the sun. And so after summer we have fall. Good. So I'm going to go ahead and put fall equinox there. And then after fall, winter. So I'm going to put winter solstice here. And then after winter, my favorite season coming up, we have spring. So I went ahead and made it hemisphere centric. So it's specific for the northern hemisphere. Okay. So know those general times too. I usually tell students I can never remember if it's the 21st, the 22nd, or the 23rd. So I usually say somewhere between the 21st and the 23rd of a month. And then I always remember December, you know, for the winter solstice, and then March for the spring equinox, and then June for the summer solstice, and then September for the fall equinox. Okay, so this little table kind of summarizes, it's a figure from your textbook that kind of summarizes for the northern hemisphere when the solstices and the equinoxes occur. So remember I said that there were certain latitudes to kind of pay attention to, and I'll try to kind of explain the significance of this. When it says vertical rays, I think if you just put direct, vertical, comma, direct. So the sun actually, sometimes it's shining right on something and sometimes it's shining kind of at an angle. So the most direct or vertical rays of the sun are hitting on the summer solstice. They're actually kind of north of the equator, 23.5 degrees. In the winter solstice, there's that 23.5 degrees south, Tropic of Capricorn. Okay. Another thing, and we'll be talking more about this, but have you guys ever noticed that, like, we were just kind of finally leaving winter. Oh my gosh, you know, December 21st or so is the time when we have the shortest number of daylight hours, right? Not only that, but if you've ever kind of gone out in December around that time and kind of watched the sun where it rises, the sun always appears to rise in the east and appears to set in the west. But, you know, near the winter solstice, it's really low. It kind of goes like this, it goes up in the sky, and then it goes like this. It never gets very high in the sky for us even. And so that kind of, we call that kind of a small angle with the sun, even at noon. Like this is noon. You're like, oh my gosh, that's noon, okay? And that actually has consequences for making us, or, you know, that's one of the reasons we're very cold. If you compare that to what's the longest day in our calendar then, most daylight hours? June, exactly. Around the summer solstice, exactly. So the summer solstice is just the opposite. It like, the sun goes, you know, way up high, you know, at noon, and then sets. At noon we're like this. So that's all, you know, something we kind of take for granted, but maybe don't take for granted. I don't know. But that angle thing we're going to kind of be talking about here that has consequences for us being cold or being warm. So here we go. It looks like the north axis of rotation is exaggerated and pointed towards the sun. So this to me looks like a summer solstice, okay, for us in the northern hemisphere. Do you see, I like this figure because, do you see as the earth rotates, okay, as the earth goes counterclockwise, yep, counterclockwise on its axis, that actually if you are above the Arctic circle, 66.5 degrees, as the earth spins on its axis, these guys have 24 hours of daylight. Okay, that's what actually this is figures over here. So, you know, we're used to seeing the sun, you know, rise in the east, okay, and set, I don't know if I'm doing this right, it's probably the other way. But anyway, we're used to seeing it rise in the east and setting in the west. But in this case, basically it would dip down, okay, so this would be midnight right here, midnight. Where's the sun? Well, it's as low as it's going to get in the sky. But then it's going to start going up in the sky higher and higher. That's what they see north of the Arctic Circle. Is that not cool or what? So anyway. Switching gears, 6 months later, right, we get to our other solstice, which would be the winter solstice. And now if you kind of focus on the Arctic Circle, up here, this is the Arctic Circle. Okay, this again, I go back to vampires, which I believe in vampires. But as the Earth spins on its axis, they don't see the sun. So that's where you gotta, because I really believe we are creatures that were meant to have light. So, the whole vitamin D thing, so that's the winter solstice for us. Okay, now the equinoxes in March and in September, the equinoxes are similar. So this could be either equinox. But the thing is as the Earth spins at all latitudes, you have 12 hours of light, 12 hours of dark. Now here's a figure from your textbook, and I actually have scratched my head a little bit on this, spent some time trying to chase it down. I'll go ahead and play devil's advocate. The thing that bothers me, quite honestly, is this right down here. They say if you are, well, what would 90 degrees latitude be, guys? What do you think? If this is the Arctic Circle, there's little dots here. This is 66 and a half. Okay, where's 90?
Maybe the poles.
It is at the poles. Very good. Ding, ding, ding. Okay, so if you're up here, okay, I understand if you're up here and the Earth spins, okay, on the summer solstice, that you're not going to see, on the winter solstice, okay, I understand that you're not going to see daylight. But on the summer solstice, would you really have 6 months of daylight? I don't understand. It's above my pay grade. I just don't understand these numbers. But actually, I've seen them. I've gone out to, then they have these naval, the Navy puts out these charts for, if you put in your zip code, they'll tell you what and it's kind of consistent with this. But aside from that crazy one, we're about 40, what did I tell you, 42, 45. So we're about here. Just go ahead, if we draw an arrow here, we can see that, our number of daylight hours is going to be somewhere between, 15 and 16 hours of daylight, the summer solstice. And here we just now kind of left winter. Okay, we're probably somewhere between, 9 and 8, 8.5 hours of daylight. So that's that. All right. So angle makes a difference. And kind of like I was standing up there a minute ago, basically what angle I'm talking about is if you take one hand and you connect it with the horizon, okay, and you take the other hand and you kind of make a vertex with your elbows, and you take the other hand and put it where the sun is, okay, that angle right there is the angle we're talking about here. And the smaller the angle, actually I'm going to try to convince you that the smaller the angle means that the sun is low, and for a couple of reasons, we're not going to get as much energy from the sun as if the angle is high. Okay. So at the summer solstice, about 40 degrees north latitude, the sun is as high as it's going to get in the sky. It's not 90 degrees, but it's 73 and a half degrees. So a right angle will be 90 degrees, so it's 73 and a half. That's kind of how that works. Okay. The other extreme at that particular latitude, which is a little bit south of us, that particular latitude on the winter solstice, at noon, the sun is only going to be as high as 26 and a half degrees. Seems reasonable. And then at the equinoxes, the noontime sun is only going to be about 50 degrees. And you guys would tell me, assuming you're not under the influence of some sort of air mass. See, now air masses move like I was telling you, and then all this we're talking about in this chapter kind of go out the window if an air mass kind of moves in on you. But you would tell me in June, equals hot, right? December equals cold. That would be like climate forecasting, okay? And then our equinoxes, so this would be either March/September, okay? That's something in between, moderate. moderate temperatures. And so notice this is the largest angle. This is the smallest angle. And this is in between. It's like Goldilocks and the Three Bears. In between. I've got one more figure to show you, and it switches from 40 degrees latitude to 33.5 degrees. Wait, no, sorry. I thought that was wrong. It switches from, instead of 40 degrees, it's 80 degrees. So just for kicks, let's find North America, 80 degrees. Well, you guys might not be able to see it, but there's a dot, 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 dot right up here. This actually is the Arctic Circle. So that's 66.5 degrees. You guys told me the North Pole is 90. Okay, so basically 80 degrees is way up. There's one more kind of solid line. I think these go over 10. Okay, so that would be like your 90 degrees. And it's kind of like we saw before. Do you see where this sun doesn't set? And they're going with the summer solstice? The sun would not set for this guy. This poor, confused, maybe happy guy if you're into sun things. Okay, the sun, this is the noon sun. It dips down to its lowest, that's midnight, and then it comes back up again. Okay, so that is like the non-setting sun. Kind of a neat little thing. So now I'm going to talk two actually. Is there three? I know there's just two maybe. Reasons why when the sun's angle is different, why does that kind of play havoc or have an effect on us with regard to temperature? And actually, they both have to do with energy coming from the sun. So there's this phenomenon called beam spreading, and you can actually kind of experiment with beam spreading if you simply have a flashlight. If you put the flashlight straight perpendicular to the thing you're shining on, that would be what would that angle be? What do you think? That angle. 90, yep, that would be a 90-degree angle. That's about as big as you can get. Okay, versus kind of putting in a slant. So this would be 90 here. That's 90 degrees. You're like, I didn't know this is geometry class. Okay, this one actually goes like this. I don't know, I'm maybe like in 45 degrees. It's hard to tell. Okay, but if you slant it down anything other than 90, then actually that chunk of light coming from your flashlight actually makes a bigger circle. Okay, this is bigger. So it's kind of like a dilution of the light from your flashlight. Okay, and this is smaller. And actually, I like this figure because it's tried to actually show you. See the smaller one? It's supposed to look brighter. And this one is less light. Well, not only is it less light, but if that's the chunk of energy coming from the sun, it's less light, it's less everything. We're going to talk about how when the sun sends us light, it sends us all sorts of different energies. Okay? So small angle means less light because of beam spreading. So I've got some examples here. This is a case where the greatest angle that can happen is being shown here in this first figure. It's showing a 90-degree angle. So there's basically no beam spreading. It's basically as concentrated as it can be. Notice the palm trees, okay? So I'm kind of thinking tropics. When we talk tropics, it's near the equator. Okay. This actually then is moving from the equator towards the poles, and we'll just pick on the northern hemisphere. So this is moving north, okay? We looked at noontime, it's quite possible that the sun won't, its highest point in the sky, it'll only be 45 degrees. And we definitely have some beam spreading. And what this shows you is actually between these two kind of shafts of light, there's 1 unit of soil, 1 unit of earth. Again now, between these two shafts of light, there is 1.4 units that it's striking on earth. Okay. If we go north even further, the sun isn't going to rise as high. And now we have this, now we have this 1 unit of light between these two, this one section of light. Now it's spread 2 units on the Earth. So that's beam spreading. The other one is beam depletion. But again, it has to do with the angle that the sun's coming through. But in this case, beam depletion occurs because the Earth's atmosphere basically removes some of the energy from the sun. So what I need to convince you with is how does angle make a difference with beam depletion? And so on this one figure, just kind of picking on, looks like one of the equinoxes. I know it's an equinox because at the 2 equinoxes, the spring and the fall equinox, this is the equator. At the spring and the fall equinox, the rays are directly overhead at the equator. So at both of the equinoxes, then we kind of have these situations with, at noon, how high does the sun get at noon? Well, at noon, if you're about 30 degrees north latitude, this is going to be the angle of the sun at noon. I'm maybe kind of liking it. It looks about 45 degrees again. And this is 90 degrees. At 60 degrees latitude, let's see if that's 90, what do you think, maybe 35? Actually, you can calculate what it would be at the equinox, but I'll just put it at 35 degrees. So here's the deal, and while I did that, I'm going to switch colors to maybe purple now. Do you see this line that your authors made? Kind of, if this is, obviously this is the Earth's surface, out to the edge of the thermosphere would be right here, out to the edge of the thermosphere. That's how thick it is. Compare that line with this line. It might be hard for you to tell, but this is deeper. I'm just going to put deeper because the Earth's atmosphere, the amount that it has to go through the Earth's atmosphere is deeper. Over here, it becomes even more exaggerated. This is even deeper. And this one up here would be deepest. And the more the Earth's atmosphere it needs, now this is at noon, right? The more the Earth's atmosphere it needs to go through, then the more depletion that will occur. So we have the greatest amount of beam depletion up there because of the thickness of the Earth's atmosphere, the least amount actually down here at the equator. Okay, so with angle, not only do you have beam spreading, but you also have beam depletion. And then my little note here is to tell you the obvious, which you guys already know. You know, if you just think of a single day, at sunrise, basically the angle goes from 0 to whatever it's going to be at noon, right? So at sunrise we have a very small angle, a lot of beam depletion. Actually, it's that thickness of the Earth's atmosphere that the rising and the setting sun go through at the low angles that gives us our cool, pretty colors in the morning and the evening. It's highest at noon, and then it goes the other way. It always also happens by latitude, and we're kind of showing it here. Okay, and it also happens throughout the course of the year. The angle changes. All right. So, different types of energy. I have a list coming after this, but we can kind of classify energy as either being in motion, and that's called kinetic energy, or it's energy that is stored, and we call that potential energy. Okay? There's different ways to chunk up energy. There are different forms of energy. And here are just kind of a few of them. Mechanical energy, electrical energy, chemical energy, nuclear energy, and magnetic radiation energy. Now, these different forms of energy, I'm trying to think, they could be either kinetic and or potential. I think that sounds right. So I want to talk a little bit more about kinetic energy than potential energy. So kinetic energy is the energy associated with motion. And as I said, my background's in chemistry, so sometimes I think of matter as just basically kind of on the little level, like little atoms, okay? And one of the things that we know as far as the physical world is that it's made up of matter, made up of atoms. Oh, I didn't put that there. Remember what that happened last time? Oh my gosh. Note to self. Okay. So all matter is made up of atoms. And the thing about atoms is all atoms are in motion. We know that. Because they move, they possess a certain amount of kinetic energy. Okay, that has kinetic energy, just kind of because of the motions of the atoms that make up that folder. I think that is so cool. So if we pick on water, which we are definitely going to have to pick on for this course, okay, what does water do? You know, well, water can either be solid ice, or water can be liquid, like we drink, or water can be vapor in the room, so solid, liquid, vapor. But all water has motion, okay? So these are kind of showing you some different possibilities of the cute little water molecules as they can move. They can vibrate, they can rotate, they can translate, which means they move from one location to another. But since water is matter, and all matter has motion, all water molecules have motion. So the physical phases of matter I just now mentioned for water, okay, we're going to kind of dive into. So this is my solid, okay, and this little box here is going to represent my liquid, water, and over here is going to be my gas. Okay, so matter in its gaseous state, let's pick on that because that's the most exciting. Water that is anything that's a gas, including water, if each one of these little particles is a water molecule, they're like way far apart. And the other thing is, I said they have motion, and I'm going to go ahead and make the length of my arrow of their motion indicate how much motion they have. So check out these gas particles. They have a crazy amount of motion. They're not connected at all, have a lot of motion. I'm going to kind of skip back over here to solids. So what do you think about solids? Are they solid water particles? Are they closer together than gas particles? Yep. So I'll still go ahead and pick on black. So down here, I'm going to go ahead and nest a bunch of them together. So this would be ice, right? Solid water. But do they have some motion? Yep, all matter has motion. So here we go. Deep, deep. Okay, so they just have a small amount of motion. They're stuck together. Now, liquids be harder for me to kind of describe or kind of draw, but I'll try to kind of draw them. The far apart's not really working for me because actually, did you guys know that most solids don't do this? Solids and liquids don't do this, but liquid water is it more dense? Liquid water is more dense. So actually, liquid water, they're closer together than a solid, but usually it's not like that. But how much are they moving? You think they're maybe moving somewhere in between the two? Yep, so let's kind of gauge the arrow. So here we go. There we go. So all matter has motion. Cute little water particles have motion. If they're in their solid state, they have the least amount of motion. If they're in the gaseous state, they have the most amount of motion. Before I move on, because actually we're going to talk about this in a minute, if you have a solid and somebody says, transform that solid into a liquid, what would you do? You heat it up, exactly. And, you know, we're going to be talking about that. So basically you add heat. What about go from a liquid to a gas?
Heat it up.
Heat it up, yep. I better say add heat. Yep. Now this is a little less intuitive, but What about if you have a liquid and you want it to go to a solid?
Cool it down.
Cool it down. Take away heat. Remove heat. Yep. You got it. What about from a gas to a liquid?
Remove heat.
Remove heat again. Yep. And actually, I like that we're using the word adding heat or removing heat. Heat actually is a quantity. Heat is energy. So that's what you're doing. You're adding energy to go from left to right, and you're taking energy away to go from right back to left again. Good. So I meant to bring in a thermometer, but since I didn't, we can just pretend like this stylus is a thermometer. Okay? So thermometers are great. You know, we stick them in liquids all the time just to gauge what the temperature of the liquid is, right? Or liquids are probably the best. You know, if you make candy, you put it in, you know, to see what the temperature of the boiling solution is. So all your thermometers do is to give you a sense. They don't tell you heat. Your thermometers do not tell you heat. Your thermometers tell you temperature. And temperature is actually an indication of how fast that matter is moving. I know it sounds kind of weird or whatever, but if you take a pot of water, so water boils at 100 Celsius, 100 degrees Celsius, 212 Fahrenheit, okay? So if you just take a pan of water, you put your little cookie thermometer in there, or, you know, my candy thermometer in there. They make cookie thermometers? So you put your candy thermometer in there, and then you watch the temperature go from, let's stick with Fahrenheit. It'll go from, I don't know, if you start with 40 degrees Fahrenheit, that'd be pretty cold. 70 degrees Fahrenheit, it goes 75 degrees, 80 degrees Fahrenheit, 90 degrees, you know, 100 degrees Fahrenheit, 150 degrees Fahrenheit. Okay, what's happening is basically you are using your stove to add heat to it. You're using your stove to pump those cute little water molecules with energy, and they're moving faster, and it's being reflected in your thermometer, candy thermometer, okay? So the whole thermometer thing is only an indication of kind of kinetic energy, okay? So temperature is not heat, an indication of heat in and of itself, okay? But I will say, kind of the scenario we just talked about, if you have a pan of water at 70 degrees Fahrenheit versus a pan of water at 150 degrees Fahrenheit, that pan of water possesses more energy at that higher temperature, okay, as indicated by the temperature, okay, but the temperature in and of itself is not an indication of the amount of energy that an object holds. Put it this way, what if at 150 degrees Fahrenheit you basically said, I don't need that whole pan of water, I'm just going to take a little thimble full of water. So now you have a thimble full of water at 150 degrees Fahrenheit. How much energy does it possess relative to your pan of water that you left behind? Okay, they're both the same temperature. Pan of water's got more mass, same temperature. It's actually got more energy, and this has less energy. So temperature is an indication of the amount of energy something has, but also you've got to consider how much mass is there. Okay, and there's a third quantity called the specific heat. But okay, so heat and thermal energy can be used interchangeably. They're synonymous. Heat and thermal energy. So when we said a little bit ago we were adding heat and subtracting heat, we were adding thermal energy and subtracting thermal energy, same diff. And one other thing you probably already know, and maybe this makes sense if you think of something that's hot going fast, literally. I mean, you can't necessarily see the atoms and molecules, but if you have a thermometer that says it's hot, those little things are going fast. Well, let's just say that you let them have access to something that's going slow. What's happening is basically these guys that are going fast will bump up against these guys that are going slow, and literally, if you've ever played pool or something like that, where you take, you have a cue ball that's going to go fast, what's it do when it hits another ball? Well, okay.
Transfers the energy.
It transfers, yeah, it transfers the energy. I'm not very good at pool at all. But sometimes it'll stop, right? And it'll go, energy will be conserved. But the thing about this one that's going fast hitting this one that's going slow is this one will just, they'll probably come to some sort of average sort of speed, which means an average sort of temperature on your thermometer. So it's kind of cool. But this is where I like to think of on these days, you know, when you're opening up the door and letting your dogs in and out at the back door, you know, like we have a fenced-in backyard. So basically, the transfer is happening from our hot, okay, I know it feels like the cold air is going in, but basically your warm air is rushing out, okay? So, well, this is a good place to go ahead and take a break, 10-minute break. Come home, come back if you want to at the bottom of the hour. So we'll start here.